hide our biggest number here. So what recursion do here is, I mean, you can do it iteratively, basically, but what recursion do here is, for every single node, you have to think about a solution. And that solution, at the end, in the root, has to give you the correct solution. For example, for 4, the 3 under the 4 is basically have the biggest element of 4. And for 7, the 3 under the 7 has biggest element of 7. So when you come to 5, the 3 under the 5 basically has the biggest elements here, here, and assumingly here. So if you compare these 3 numbers, one of them should be the biggest one, and we can just say, okay, the 3 under the 5 basically have 7, 5, and 4, and 7 is the biggest number. When it comes to here, it's the same thing. 3 and 15 checks 15 and 3, and it says, okay, 15 is the biggest number here. And 6 checks 7 and 15 and 6 itself, and says, okay, 15 is the biggest number. So basically, we didn't try everything, but we said, if our left node and right node returns us the biggest values beneath them, we can just compare them to myself and get the biggest value. And this solution basically works for every single node here. So implementation is quite easy. Let's go ahead and do that. I will write on C#, sorry. It will try to find a maximum value. So if our node is null, if basically we should consider these cases too. If our node is null, basically we should return the minimum possible number to, because when we compare the numbers coming from here and here with 7, we should find 7. So if node is null, just return the minimum value. If node is not null, we can compare this left node, right node, and the node itself. So return maximum of the node's value itself and the left side and right side solutions basically. So this is not a function. So we can compare 3 numbers in C#. I don't know about other languages, so we have to do it again. Basically, that's the code to find the biggest value. So, any questions about that? Any interesting thing you could discover when you are looking at this code? Perfect. So,
Murad,
yes.
what's the important? If node equal to that, return infinite value.
If node is null, we basically want the minimum possible value to compare with. For example, here 7. These 2 nulls and 7 are going to be compared. So we want the minimum value possible from nulls, so the 7 can return.
So
smallest integer possible.
Yeah. So if this is clear, I want to, some of us solve this question. It's in progressive, but it's actually a really good implementation of recursion. So it's longest univalley paths. Basically, we have another binary, so binary tree, and in that binary tree, we are trying to find the longest univariate path. Univariate path means like all the elements in the path are consisting of the same numbers. So check the example. So in here, for example, we have 1, 2, 3 5s in paths, and we have 1, 4, 1, 1, and 1, 1 paths. So basically, we should return the longest univariate paths size, which is 3. If we had something like 3, 3, 3, 3, 1, 3. In here, for example, 1, 2, 3, 4, we can return 4 because the longest univariate path is 4 here. Any edge cases other than anything does it? I don't think so. It's basically that's it. We should be careful about going right and left. And other than that, for example, if we had another 3 here, this won't change anything because this path is 4 and this path is 3 and this path is the already one we found. It's also 4. That's it. So anybody has, I mean, those who wanted to take the recap. So do you have an answer for that? Do you have an idea for that?
I mean, the example it says 2.
I think it returns 1 minus 1. I think. Yeah, it's counting edges basically. It's the same. I was thinking that I was only going to. Okay, Abba, do you have an idea?
I mean, I had, but I just got counter now.
By yourself? Okay. So, what we can do here, basically, recursion helps us to solve smaller problems that we don't have to deal. So, in here, for example, if we are in a node, we can say, let's count here. Okay, we are on this node. And we say, okay, so this node is 3. Are there any paths from the left, coming from the left, which is 3, which basically contains 3? Are there any paths coming from right, which contains 3? And basically, for example, here we have a left path. It's actually there, this one. Here we have left path. This one, its length is 2. And here we have right path, its length is 1. So if we have here 3, 2, we can say we can merge these paths and add this 3, 2. So 3, 2 plus 1 plus the node itself, it will be a path of 4. If we want to send it to a parent node, we also keep track. We also should keep track. Okay, this here comes 2, so this will make it 3. Here comes 1, so this will make it 2. So we should return the parent, the biggest one, not this one. That's the main logic basically. For every node, if we apply this, we can get the answer on the root. No, not on the root, we should keep a global variable and check if the path we find is the biggest one. So, if we try to implement it, how should we name it? Longest univariate path. if our node is null, we don't have a path at all. So we can basically return zero. If our node is not null, we should gather information from the left and right node. So we can say left path, and left path will call this recursion function again, and it will gather information from the left node and also we should have a right path, and it will gather information from the right. And for example, in this case here again, so we had 3 here, 3 here. So we are assuming that this will return us 2 and this will return us 1. So what we can do is, first we can say that if okay, first we check if the left node is null. And wait, I think we can do it in a better way. If it returns true. I can come with another thing, so I will just check the. If the both nodes are null, basically our path is 1 itself.
I think that I don't think you need to check that. Because, I don't think you need to check that because if the left and the right both return 0, then you're gonna have to add yourself on top of that, right?
Yeah, but we are trying to check the left value and right value, are they equal to our node's value? So when we are trying to check that, we should also check left node. So if the left node is still null, this means that right node is not null. So we can check if our node's value is actually equal to right node's value. And if they are, we can say we can add 1 more to right path. So we are saying right node's value equals to our node's value. If is that so, we can return right path. Plus 1. Otherwise, we should return 1. And it's also same for the right node too. If right node is null, in this case, we can say if the left node's value is equal to our node's value, we can just return left path plus 1, otherwise the node itself. And if they are both not, basically we are returning values from here, so return, we don't have to write it out here, as here. So we have to check Okay, so if our node value and right node value and left node value is equal, if they are equal, you should add one more to left path because left path coming from left can be added one more element, and we say, oh, we are just saying, oh, we can actually do it here, okay. If they are not the same, we don't add anything.
Same goes.
Same goes for the rights. And after that,
Your global variables,
sorry?
global variables to check the maximum.
Yeah, we are actually, right now I am trying to find out a better code to do something. Okay.
Or you could pass the maximum value to them.
No, I get it, I get it. So, we have the left path, we have the right path, and so we are going to check. So actually, these are maybe unnecessary. Okay. So, what we should return is basically biggest of one of these, maximum of one of these. But also we should check the maximum value. Okay. So, if both values are node value, I will just write it down like this. We should compare our global max number. The summation of left path, right path, minus 1 because we added the node itself twice in that case, and the max itself. And other than that, we should also compare the max with left path. Basically, biggest sum of left path and right path. And max itself. And we should return the bigger value of left path and right path. No. Okay, so what we should do here is basically, if the node's value is not equal to left node or right node's value, we should make this left path basically 0. So minus left path. and minus like that. And return the bigger one. Yeah.
In this case, are you counting the nodes or the edges?
itself, yeah.
Sorry?
Are you counting the nodes or the edges?
No, not nodes.
Okay, if the
Just return the maximum minus one. Yes.
okay, okay.
So this doesn't find the longest path, but max does.
I was thinking maybe what if we pass as a parameter what the parent is,
But the parent is. Okay.
and when it checks if the node is null and if node is null, or if the current node is not the same value as the parent, then it just returns 0. In that case, it covers the end cases, and maybe you don't have to check if it's null or not.
So parent
I don't
works
know
for
how
us
that's
how?
set up. What?
How does parent work for us? What is the use of parent?
The parent sends its value,
Uh-huh.
and the child just checks if it's the same value as the parent.
Uh-huh.
And then it returns to the parent how many of the same elements are there. But if it's a different value, then it will only work from down from itself, and it just updates the max. But if it's different from its parent, then it just returns 0, and the parent decides on
Okay,
what.
this sounds clear.
It checks if it's 3, then it keeps going, and then returns that value, like max of the left and the right.
Does it calculate the right path too?
Yeah. It does calculate for itself, but it only returns it to the parent if it's the same value as the parent. I don't know if this is working, I'm just suggesting.
I actually didn't get it, so.
Let me try to show you. So, in this case, this parent, I don't know how we start. Maybe we can give it null, and then maybe, we need to check. So in this case, this parent calls the function on this one and tries to get a number of paths for its own value, like for 3, right? So it passes 3 as a parameter. And then this one gets it, and if it's null, definitely returns 0, meaning if it's at the end. Also, if it's a different number, in this case, for example, if this is a different number, it just returns 0. And this one gets that there's 0 elements of data, that there's 0 paths. I mean, a length of 0 is 3 value exists, and then it just keeps returning, adding to the 0 and going on. Does that make sense? Like, my point is, we won't have to check if the left exists and which one doesn't.
I mean, that makes sense, but I'm not sure how the implementation would look different.
Okay, in this case, we just add an OR, and if it's not null, then we also check if the value is the same as the parent's value, and we just return 0.
So
If
parent,
it's
we
not,
should also check the parent value.
the parent could not be null. The parent is always the root. We just give it maybe if it's we give it a number that doesn't exist in the list. Maybe it's out of bound. Maybe it's null. Yeah, we can check that. And this handles if these cases, if it's equal to, I mean, if the right child and the left child are the same as the root. Like that whole thing is how it happens right here. The child checks the parent only once. Like, you don't have to go this side and this side and check separately.
In the left pass, that's equal the ternary function. Should we be, we're adding 1 if left and root are equal, right? What's the second condition? Left or right?
Oh, by the way, this shouldn't return. I mean, we still need to check, but when we return, we check if the parent value is the same and we return 0 in that case. So this shouldn't return, sorry. No, it shouldn't return here, it just check. I mean, if it's null, of course it returns here, but it checks later if it's the same value as the parent, and it returns 0 if it's different, and it returns it has its found if it's smaller. And then it also updates the max. Since it's already global, the max shouldn't be there. I mean, at each time, the value you get would be the pad that's below it, and then you try to update it with 2, and if 2 is the maximum now, and it also checks if its value is greater than if its value is the same as the parent, and it returns 2 in this case. But in this case, it checks, it tries to find a pad of 1. This is different from it, so it just returns 0 for it. It gets for itself length of 1, and tries to update the max, but it doesn't return it, since it's different from the parent. And the parent gets 0, and then it gets a value of 1 in that case. It tries to update with the max, it's still not lower, and it still returns 0, it doesn't return the values found. And this checks, it's already, and this one tries to find a different path, it finds 1, and since it's the same as the parent, it returns that 1. And this one has already 1 itself, and realizes there's another 1 coming from it. And then it realizes it has 2, and maybe it's different from the parent, so it just returns 0. I mean, the parent we give it could be a null at the beginning. Since it is different, it just, like, since we're just doing a value check, if it's equal to or not equal to, then it doesn't matter if it's null or not.
So we found 3 and 2 here. And we should
Yeah.
find 4. How do we find?
What do you mean 3 and 2? Like in this case, we found 2, including itself is what I have.
In this case, coming from it, we found 3.
Yeah.
But we are trying to find 4.
Okay, let's just ignore itself, and then let's just say it's found 1 from this side, and then it's found 2 from this side. You can pick the maximum to 2 and add 1 to it. I mean, and try to merge them, I guess.
So basically, you are actually getting the left and right values,
Yeah.
and you are also using a parent.
So we do need to check if the values are the same too, yeah. But if it's 0, then I just thought it would reduce the checks, but
It might be logical. I have to see the calculation basically. I can't imagine. So I think this might be -1 because we should at least have f of 1, and that's okay.
Are we returning -1 because the loop is
We are going to return 1. If we subtract from left path -1, we will have 1. Yes.
Murad?
Yes.
I still don't think we need to check the left and the right, because like if a number other than 0 is given to you, then you know that the left child or the right child is definitely the same value as you. So you won't have to check that. Not in this case, but in what I said.
Okay. Yes, sir. So, I mean, is it definition clear to everybody? It's a very long code, but basically, this is a case, this is a case, this is a case, and this is a case. If the both nodes, left and right, are actually existing, they are not null. We check the left and right values, and basically, what we are trying to do is trying to find a, if they are same as the nodes value, we can basically sum up them. 2 coming from here, 1 coming from here, and nodes value is here same. So 2 plus 1 plus 1. We are checking it with the maximum. Other than that, we return the longest path, basically 2 from here, 1 from here, and this nodes value are the same. So basically, we should return 3, the biggest 1 plus 1. And yes.
What if instead of keeping a global variable, we passed it around in every function call?
And we can just do something like reference. And that's the same. We don't need this. But also we should add them here and here.
And we should check that, yeah.
Basically that's it. Thank you for listening.